Hello and welcome to this recapitulation of a presentation I originally gave at the INCOSE International Symposium in 2013 on functional architecture as the core of model-based systems engineering. This was a presentation and a paper that you can find in the Wiley and COSE library, co-authored with Barbara Sheely at the Boeing Company. And since I'm doing this in 2024, I may be making some references to other presentations that are on the YouTube channel. So what I want to talk about is the role and benefit of functional architecture in the development of system architecture and requirements and other things. And what we found is that functional architecture really spans the totality of the life cycle of any system, from customer need to architecture definition, including requirements, through integration, verification, validation, and operations and maintenance as well. So we'll talk a little bit about the motivation for why we want to do this. This graphic is a representation of what you may have seen in MIL Standard 499 and some other earlier systems engineering definition activities. But what we found is that functional architecture, including analysis and allocation, is really at the intersection of the internet engineering problem and the solution space. So the motivation arises primarily, or first, from the fact that system engineering is primarily focused on system behavior. Most engineers concentrate on what the system is. Primary focus of systems engineers is on what it does and why it does and how well it needs to do it. So we derive requirements from the system mission and the associated functions and their related performance. And I've got a number of papers on the YouTube channel that are related to that. Excuse me. And then we derive system elements and interfaces from the requirements to ensure that they actually are going to be able to satisfy the requirements. Integration is going to be focused on the capability of the integrated system to perform those system functions and mission threads, those elements of the system working together. And verification and validation prove out what it does. Verification that it satisfies the requirements, and validation that it satisfies the need. And at the time I was working at the Boeing Company, and we were emphasizing functionality in the architecture definition, not just the logical architecture. So what is a functional architecture? Well, this is a definition in the old IEEE 1220 standard, which has been superseded by something else. An arrangement of functions and their subfunctions and interfaces, both internal and external, that defines execution sequencing, conditions for control or data flow, and the performance requirements to satisfy the requirements baseline. And some of these elements you may have seen in other places, and their representations in various methodologies and languages and tools. But the ideas are that functions are decomposable into subfunctions, and we talked about that in a related and linked presentation that you can find about two different kinds of decomposition. So this is the second type, functions decomposable into subfunctions. Actually, it covers the first type as well. Interfaces, the control flows that control sequencing and decision logic and which function you perform, decisions about which function you perform next. Data flows, which are about information exchanges, and all their associated requirements that enable you to describe input-output transformations in order to accomplish the mission and satisfy user and other stakeholder needs. Ultimately, we're satisfying the requirements baseline as it's handed to us, but we need to, of course, validate that, not just launch into an attempt to satisfy requirements, but we want to make sure that the requirements are validated, and there's a number of presentations on the YouTube channel about that. So elements of the systems engineering lifecycle that are impacted by the functional architecture pretty much everything. So if we think about what is it a system does, that's related to its mission. And from that, we define and analyze requirements. We can perform fault or failure analysis. We perform trade studies. We have interface definition. We'll talk about how that's derived, and then analysis of interfaces, and then control of interfaces, a configuration management function, and then architecture definition and allocations that include all these things about functions and subfunctions and interfaces. Then we get to integration, verification, and validation. We can actually use the functional architecture to help us with our planning and procedure definition, analyze risks and issues and opportunities. And then in operations and maintenance, we can actually develop operator procedures and allocations and examine any issues and opportunities during operations and maintenance. So the availability of a functional architecture is extremely useful over the totality of any system lifecycle. So I have a series of slides that go through each of these. There'll be a little table where the first column is what's the system-related systems engineering process, what's the benefit from having an available functional architecture, and what are some of the consequences if the functional architecture is not available, and I may include a graphic that attempts to highlight one or more of these issues. So for requirements definition, we ought to be deriving requirements from the functional architecture. And again, I've got a number of papers about that, and the related measures of effectiveness. That's the operational analysis. Here's a graphic cartoon of some analysis that we had done back in 2004 and 2005 that allowed us to identify what are some key system requirements in order to enable a particular kind of operational architecture to be successful. If we don't have the functional architecture, then we're not going to be able to validate or justify the requirements. We're largely guessing that the requirements we've defined are going to work. In other words, they'll be able to satisfy the concept of operations. But we're not really sure unless we've got a simulation. And so that's one key common thread through this presentation, is the importance of being able to use the functional architecture to perform system simulation. Another piece that's extremely important and sometimes gets lost is the ability to clearly delineate operator tasks from system functions. Because when we define operational tasks, operational activities, that includes some combination of what an operator or user does as well as what the system does. We typically allocate particular functions to the system. Concurrently, we should be capturing the related operator tasks, but often that's left to some later activity. And so we lose the benefit of that initial analysis, and we end up with duplicate or rework during development of training materials when we must define what the operator tasks are. So an important activity, and the architecture framework models are basically set up for this very well, be able to define operational activities and clearly decompose them into system functions and related operator tasks. What's the operator doing? Providing inputs and receiving outputs. And there's clearly some interaction across some system to operator interface or set of interfaces. And we can use the functional architecture to capture those things as we're developing the system definition. So this is extremely powerful, and it enables us to capture what the operator must do early on rather than waiting for just training development when the system is all defined. The larger topic of requirements analysis, clearly we want to derive requirements from the system functionality, related performance. And if we have a functional architecture, we can do that and test for completeness. And you can see some of my other videos on the channel. If we don't have the functional architecture, we're likely going to be missing requirements because our derivation of requirements is largely a decomposition of parent requirements without considering all the functional and system behavior related to that. We can also find inconsistent or missing allocations because we have a functional architecture or system model, and so we can avoid gaps and conflicts of functionality, and this is validated by having a simulation. For this lower section, the key benefit of the functional architecture when we're doing the functional analysis is clearly identifying the verbs that are going to go in the functional performance requirements. And if we don't have requirements derived by that method, then we may not be able to fully justify the requirements we have. And so this is a graphic from a paper by Pereno and et al. From 2001, where they show that the functional analysis and related information can be used to auto-populate a template for how to write a requirement. So, and we built on this idea in our 2015 paper on implementing structured requirements. The other part of this is we can identify states and modes as conditions that will be used across many requirements. And one clear benefit is we can identify not just modes where particular functions are required, but we can also identify modes where particular functions must be prohibited. And this is not always addressed in many system developments, and they're only found out when there's some sort of a tragedy. Anything where we don't have a specific need, we might say, well, it's allowed. And if it's allowed, it means it's not required and it's not prohibited, so we would probably not write a requirement about it because it's not required. But the table allows us to be explicit and complete about the allocations of functionality to different modes of the system that may occur in one or more states of the system. So this was what we called a mode performance table, which we found to be very useful in generating material to be able to write good requirements. Another key feature of having a functional architecture is enables us to be clear about the system boundary and the external interfaces, moving from a functional context. This is the IDEF 0, A-0 diagram, which is focused on functionality. What are the key inputs? What's the key output related to the mission? What's the allocation? What's the function? Also relates to deriving the context diagram, the logical interfaces in the context associated with any logical element, the system of interest. And clarity here is extremely important because it's these boundaries and interfaces that allow us to validate the requirements that we're deriving. If we can't observe a function at the interface of the system of interest, then it's not going to be verifiable at that level. And so we probably have some sort of an error. It also clarifies where the interfaces are and helps us avoid disputes where different stakeholders, principally acquirer versus supplier, have different concepts of what the system boundary is. So these types of diagrams are extremely useful, and they arise from a functional architecture as well. We can also use the functional architecture during requirements development to clearly decompose those interfaces at the system of interest boundary for individual requirements. So we might describe in the context operator commands to some sort of a system. In this case, it's for a vehicle, road vehicle, but that gets decomposed for specific other functions like inputs for acceleration and braking and steering. And these get manifested and documented in the functional architecture so that we can be clear in the requirements and in the interface definition about what the system is supposed to do. If we're not clear about this, then we may have late discovery of those interface details, the requirements not related to the interfaces, and conflict with the interface partners about exactly what the characteristics of those interfaces are. So we want to avoid those future conflicts by defining things up front. The other benefit is when we organize our functionality this way, we can use that to help us write logical requirements and organize our specifications related to functionality. In fact, I used to tell people that you can write your requirements directly from your functional analysis because it's telling you what the inputs are, what the outputs are, what the sequence of events is supposed to be. And that's extremely useful, not just a random collection of individual requirements. One of the things I've worked on over my career is fault analysis or failure, and I focused on functional failure. You may recognize this diagram from the very first SRA1 paper from 1995. What to do with respect to any function if some conditions related to that function aren't experienced. What do you want to do when it doesn't have the right inputs? So functional architecture enables us to analyze both nominal and off-nominal behavior, gives us an opportunity to address what if, and you can also, if you've got an executable model, you can inject failures and see what the system does under those conditions of failure, or different inputs, or unexpected inputs. In the architecture, we can identify inherent hazards, behaviors that we hadn't expected because of the interaction of system elements, as well as the response to failure. So fault detection, isolation, and recovery, we can examine that during the development phase before we get to integration and fix any design issues before we get there. The last thing is we can also have an executable model, and this is a communications model that we developed. We can look at, well, what happens if the message doesn't get through? What do you want to do? In this case, we had a couple of possible responses. But the point is you can analyze these things before you actually build it because you have it in the architecture model. This is extremely helpful in making integration and verification go more smoothly. Clearly, another benefit is examining different architectures, and that's what we call trade-off studies or trade studies, where we can attempt to optimize any particular system architecture with respect to the measures of effectiveness and including measures of suitability. So there's generally more than one possible solution, and we want to examine different alternatives before we make commitments. And having a functional architecture allows us to do that. We can both decompose the system level functions, but then also allocate them in different ways to different logical architectures. And I went into this in some detail in the discussion that's captured in the linked presentation on the YouTube channel on the two kinds of functional decomposition. So this would be an expected benefit of having a good model of functional architecture, and you would end up with two different architectures here below the system of interest level that you could then use that to examine which of these architectures at the next lower level is preferred with respect to your system measures of effectiveness. Another benefit is the ability to derive the definition of interfaces from the logical architecture and the functional allocations. So in this graphic, we're showing that if we've got two different functions that are allocated to two different systems, well, clearly there's got to be a functional interface between those two different functions. Some output becomes some input. But given that these functions are allocated to different next lower level elements, we now identify that there has to be a related logical interface to be able to convey this function, in this case electrical power, not only from one function to another, but from one subsystem to another subsystem. So we can use this functional architecture in a disciplined manner to justify all the definitions of interfaces, both functionally and logically, and we can link these interfaces to the functional requirements. Say you've got to deliver electrical power in this example in accordance with some definition that is captured in interface control documentation. And that allows us to capture that definition at the same time we're developing the requirements. And so there's a clear relationship then between the functionality, the related performance, and the interfaces. And then all parties to that interface are represented in that interface control definition. And this can be useful not only in the definition aspect, but in the lifecycle maintenance of that interface definition. So we can validate the interfaces because we know there is some functional relationship. Those are allocated to logical elements. Also help us understand the degree of coupling between logical elements. And this would be examined as part of trade studies to determine whether there might be a better alternative than something that like high interface coupling that creates dependencies that may lead to problems during development, during operations, during lifecycle support, and so forth. Interface control, one benefit of having a good functional architecture, and one thing that we demonstrated in our work at the Boeing company was being able to publish interface control documents directly from the architecture. Rather than manual generation and transcription where you're copying engineering data from one place to another, simply use the functional architecture to directly publish the interface control documentation. That way, when there's an update to the functional architecture, you can also update the interface definition at the same time and maintain consistency among requirements and interfaces and interface control documentation. So this is an important configuration management capability so that you can manage those changes over the life cycle and ensure you've got consistency going through the normal configuration management processes like an engineering review board and so forth. Functional allocations become more clear when we're able to identify the logical elements, the system level function, and then the functional allocation, subfunction allocation, and then derive the related functional performance requirement associated with that function and allocated to the logical element. So it's an easy way to be able to validate those allocations and also ensure that that allocation is going to enable the system level function and its related performance to be satisfied based on those allocations. Another area of allocation and validation is reliability. So we can decompose the functions and examine the allocation of reliability in order to achieve the reliability of the system level function. And then these subsystem reliability allocations can be validated by potential solutions to ensure that we can actually satisfy them. And if not, then we have a couple of options available to either revise the architecture, logical architecture, or attempt to improve the logical element reliability in order to achieve the functional reliability. But this is an area that typically doesn't get enough attention early on, in part because we don't have the tools or we don't have the information available in the functional architecture and use it to actually validate that we can satisfy system level reliability requirements based on the allocations. We can also use the functional architecture to help us with our integration and verification and validation planning and execution. So in implementation, we can auto-generate the solution from the functional model. This already happens to a degree in software. We can also, during transition and integration and verification, generate specific use cases for planning the incremental buildup and deployment of the logical elements and the associated infrastructure, the elements in the context, external interfaces, simulation of any particular external interfaces, and the sequential satisfaction of internal interfaces based on the availability or non-availability of specific logical elements. We can also use the functional architecture to generate use cases for procedures that we'll use during integration and verification, because we have not only what the system is doing, but what the inputs coming from the outside have to be, and those can be built right into the procedures. In fact, you could generate the procedures directly from the functional architecture. What is the sequence? We can also, ahead of formal verification, use a logical model, functional architecture, to analytically verify that the architecture is going to satisfy the system requirements based on simulation of what we're doing. And that has potential benefits in terms of lowered program costs, because we may be able to use the model to actually perform the verification in lieu of testing. And that's often a much lower cost to the program. So if we can demonstrate, we can prove the system satisfies its requirements, at least some of its requirements, by analysis, that's often cheaper. And if we've already built the analysis model in the functional architecture, there's really not much extra cost to simply exercising it in order to prove that the requirement is satisfied. We can use the functional architecture during integration and verification to help manage risks by first confirming the expected behavior, the functional architecture, before we go to integration and verification, rather than using integration to discover actual behavior and then redoing the design and implementation for any unexpected and undesired activity or functionality. We have a clear association of interfaces to functionality, so we can examine and understand the effects of interface discrepancies and fix them before we get to integration and verification. And we can also identify areas of integration risk due to, for example, concurrent functionality, critical timing relationships, required and versus prohibited states and mode dependencies. So we can consider the potential risks of the design ahead of time and make sure that that the architecture is going to be fit for use, and we'll be able to get through integration and verification with a minimum amount of delay and rework, because we've already demonstrated in the model that the system does what it's supposed to do. Issue management is a common problem because problems always arise during integration and verification. So ways we can use the functional architecture is to aid replanning when logical elements are not available. Okay, we have a subset of what we need. What can we do with it? What could we prove? What could we integrate? What could we verify? And so we can get more benefit of the equipment we have, not just wait for new logical elements to arise. During verification, we can provide information for functional performance reallocation if we find there's any deficiencies identified during verification. You can examine the architecture model, make changes, see what might work better before we go to implementation. We can also use the architecture model to help resolve anomalies, things that we weren't expecting, and fix them ahead of time, rather than simply forcing the stakeholders to accept the system as is or go to rework based on just fixing the anomaly without really understanding the root cause. And in validation, you have an opportunity to exercise a functional architecture to examine extended capabilities for additional user needs ahead of operational test and evaluation to be sure that the system actually will yield the capability that is needed by the various stakeholders. So we can decompose the system, and then during integration, we put those things together. And if we have an architecture model, then we can examine that before we actually get to the physical integration. Also, we can, during validation, as part of opportunity management, predict additional capabilities based on the exercising of the model by analysis ahead of that operational evaluation. So we may find out that we have additional system or system-of-system capabilities that we can analyze analytically, what we call virtual experimentation, if you will, ahead of time, which can save us a lot of money and help us identify areas to focus on for additional opportunities. Another key benefit during operations and maintenance, or to support operation and maintenance, is being able to develop and derive and yield operator procedures directly from the functional architecture. The sequences, what is the system doing, but also what are the operators and maintainers doing? And I used the capability of the functional architecture in an MBSE tool in my graduate class to auto-generate and teach the students how to auto-generate these procedures directly from the functional architecture, as long as you have a complete model that includes what the operators and maintainers are doing. So this can save a lot of time, and it can also ensure consistency in the procedures that are generated, because they're generated from the same model as the system architecture. Additional issues and opportunities during O&M: we can analyze operational problems by simulation using the functional model, rather than just having to exercise system hardware. And maybe you call this a digital twin, to use some more modern language. We can identify revised or new functionality allocations when we have, for example, diminished manufacturing sources as things become unavailable, or we want to perform some technology insertion or refresh. Make sure that the revised functional architecture is going to be effective at meeting the system requirements as well as the user needs. We can also use the functional architecture to help us with our product line management, where we have subtle differences or significant differences in different elements of the system for different users or different specific needs. Make sure that we can identify any gaps in the capabilities that are desired. So this is another way to use the functional architecture during operations and maintenance phase. So in summary, we say that focusing on the functional architecture yields benefits throughout the life cycle, and that is certainly enhanced by having your functional architecture and a model-based systems engineering tool database. It begins with what are the user needs and the missions and related requirements, what the functionality and related performance, the requirements analysis that follows from that. That includes definition of boundaries and interfaces and consistency of the requirements and the allocations to elements of the logical architecture. We can use the functional architecture to help us in our trade studies, to examine the trade space and enable us to look at multiple architectures to at least select a preferred one, if not exactly optimize over all possibilities. We can use a functional architecture to help us with our fault management, earlier analysis of functional failures. We can use it in our architecting to have clear requirements allocations and consistency of the interface definition management. And we can use it in integration, verification, and validation planning to develop procedures and perform revisions when we have difference in execution of procuring elements of the system versus our planning, making sure that we have all the interfaces identified and simulated and available as needed. It can help us in our execution to ensure that during integration and verification, we can actually prove that we satisfy certain requirements by analysis, and we can also examine impacts of changes or non-compliance to be able to see how we can revise the allocations and or performance to enable us to achieve a system that satisfies all its requirements. Finally, during operations and maintenance, we can use the functional architecture to define the operational procedures directly from the architecture and also analyze opportunities and resolve issues. So with that, I will end here and be happy to receive any comments you want to make on this presentation. So thank you very much for your attention.